Hello, welcome to lesson 13. In this lesson, we are going to look at the compound microscope. A compound microscope consists of two converging lenses of short focal length. And this enables a high angular magnification to be obtained. If the focal lengths are small or short, that is, then we are going to have a higher angular magnification. So usually these compound microscopes are used in the laboratories. These are the microscopes you usually see in the laboratories being used for viewing small objects. In normal use, the objective of a compound microscope forms a real inverted image of the object at a distance less than Fe. That's Fe is the focal length of the eyepiece, at a distance Fe from the eyepiece. And that image which has been formed, which we call the intermediate image, acts as a real object for the eyepiece, which thus forms a final virtual magnified image. And the image is at a distance, or what we call the least distance of distinct vision from the eyepiece. Let's see what we are talking about. So this is the object at O, there is an intermediate image here of height h1, and that intermediate image is at a distance less than Fe from the eyepiece. This is Fe, the distance from here up to here is Fe. And this image, the intermediate image, acts as the object for the eyepiece, And then the final image is going to be magnified, and virtual, and actually inverted. And it's going to be a distance d from the eyepiece. That d is the least distance of distinct vision. So when we look at this, the angular magnification can be got for this compound microscope in normal adjustment. Let us try to derive that angular magnification. So first of all, we need to know that angular magnification is defined as the ratio of the angle subtended by the final image onto the eye when using an optical instrument to the angle subtended by the object onto the unaided eye. So it is going to be alpha, m is alpha divided by beta, where alpha is opposite h2 divided by adjacent, which is d, since alpha is a small angle in radian. So we shall have it as h2 over d, and then our beta is going to be opposite, which was h over d, and that will give us the angular magnification of the magnifying power as alpha divided by beta, and that will be h2 over h, which can be written as h2 over h times h1, h2 over h1 times h1 over h. This does not change the meaning because the angular magnification we have seen as h2 over h. I can write this as h2 over h1 times h1 over h. But as we can see from here, we can clearly see that this h2 over h1 and this h1 over h are actually that ratio h2 over h1 and h1 over h2 are actually linear magnification of the objective lens, of the eyepiece lens and objective lens. h2 over h1 is the linear magnification for this eyepiece, and h1 over h is the linear magnification for this objective. But we know that the linear magnification of the objective is going to be given us, for the objective, is going to be given as V naught over F naught minus 1. And then for the eyepiece, is going to be negative, if we consider then, because that's a negative distance, it's going to be negative of D over F naught over Fe minus 1. So when we substitute, we shall have our magnification as negative of d over fe plus 1 into brackets v naught over f naught minus 1. This d, we shall substitute this d, we have already considered the sign convention. So if you're applying this formula, again, we don't need to consider d as negative, since you have already, when you're deriving the formula, you have already considered it as a negative value. So when you're substituting in the calculation, we just substitute the value, not in considering the sign. Let's make a note here that it can be clearly seen when you look at this and that. When you look at this, that if fe and f naught are small, then the angular magnification is going to be bigger. From this expression, you can see that when fe and f naught are small, then higher angular magnification will be obtained. Let's look at compound microscope with the final image at infinity. This was when the final image is at a near point. But now I want to see when the final image is at infinity. The objective still is going to form a real inverted image of an object, but this time round it's going to be at the principal focus. That final image, that intermediate image, is going to be at the principal focus of the eyepiece. Let's see what we are talking about. So the intermediate image, this image of height h1, is going to be at the principal focus of the eyepiece, and because of that, the final image is going to be at infinity. When this is at the principal focus, the final image is going to be at infinity, because the object is at the principal focus. And we can still get the alpha, which is going to be, since alpha is a small angle in radians, alpha is going to be approximately called tan alpha, which is going to be opposite as h1 divided by adjacent, which is fe, and that will give us h1 over fe as the alpha. But remember, our beta is the h over d, so it implies that the angular magnification or the magnifying power is going to be alpha divided by beta, and if we substitute, we shall have it as h1 over h times d over fe. But this h1 over h is actually the linear magnification for the objective, which is given as, in which case that h1 over h is the m, the small m, the linear magnification, which is given by v naught over f naught minus 1. So if we substitute this one here, we shall get the magnification of this compound microscope when the final image is at infinity. So that will be the angular magnification of the magnifying power. So just put this here, and then you shall get the m. Let's look at the differences between a compound microscope and a telescope. A compound microscope consists of two. We want to look at. We shall not look at it in terms of definition, but let's just look at what each of it does. First of all, we need to know that a compound microscope is used for viewing near objects, while a telescope is used for viewing distant objects or objects at a far distance. Then also we need to know that for compound microscope, the objective of a compound microscope has a short focal length, while the objective of a telescope has got a long focal length. And also, in normal use, a compound microscope forms a final image at a near point, as we saw, while for a telescope, the final image in normal adjustment is at infinity. We shall see that when we look at telescopes. Let's look at some examples. 1. The objective of a compound microscope has a focal length of 2 centimeters, while the eyepiece has a focal length of 5 centimeters. an object is placed at a distance of 2.5 centimeters in front of the objective. The distance of the eyepiece from the objective is adjusted so that the final image is 25 centimeters in front of the eyepiece. Find the distance between the lenses. Find the distance between the lenses, that is the separation between the objective lens and the eyepiece lens, and the magnifying power of the microscope. So we have that question. So in this case, they are saying the final image is at 25 centimeters, so it is at a near point. So the final image is at a near point, so that means that this compound microscope is going to be normal adjustment. So if you look at the ray diagram, when the compound microscope is in normal adjustment, we shall have it like this. So this distance is 25, this is 2.5, the object distance for the objective lens, and then this is going to be V0 for the image distance for the objective lens, and then the image distance, and then this UE is the object distance when considering the eyepiece lens, and this is the final image distance, which is 25 centimeters. So we can get this separation by adding V0 plus UE. So we need to get UE and V0. So how do we get UE? UE, we can, remember we have F here, we have the V. So we can get UE using the formula. So we consider the action of the eyepiece, we shall have VE is going to be negative 25, and then F is 5. So using the formula 1 over F is equal to 1 over U plus 1 over V. When we substitute and make UE the subject, we shall get our UE as 4.167, which is approximately 4.2 centimeters. Let's also get V0 using this other lens, that is the considering the action of the objective lens. U0 is 2.5, V0 is not known, we are looking for it, but F0 is 2 centimeters. So using the lens formula, 1 over F is equal to 1 over U plus 1 over V. Substitute, considering the sign convention, we shall get our V0 as 10 centimeters. So it means that the distance between the objective and the eyepiece is going to be V0 plus UE, which is 10 plus 1.2, sorry, 4.2. So 10 plus 4.2, which will give us 14.2. So 14.2 centimeters is the required separation. Let's also get the required magnifying power using the formula. So we substitute that, where actually the D is 25, the D is the 25, D is 25 centimeters, and the FE we know as 5 centimeters, F0 is 2 centimeters. When we substitute, we shall get our D, so sorry, we can get our magnifying power as a negative 24. So we shall neglect the negative there and conclude that the required magnifying power is 24. Let us also look at this question. Lastly, a compound microscope has an eyepiece of focal length 2.5 centimeters and an objective of focal length 1.6 centimeters. If the distance between the objective and the eyepiece is 22 centimeters, calculate the magnifying power produced when the image is at infinity. So here we need to consider when the image is at infinity. This is when, so we know that when the image is at infinity, the intermediate image formed by the objective lens is going to be at the principal focus of the eyepiece. So this is what you are going to be having. The intermediate image is going to be the principal focus of the eyepiece, and therefore the distance from that intermediate image up to the eyepiece is going to be 2.5 centimeters. So if I want to get this V0, the image distance for the objective lens is going to be 22 minus 2.5. So the analysis is what I'm talking about there, that for the image to be at infinity, the object must be at the focal point of the eyepiece. And so we shall get our image distance for the objective lens as 19.5 centimeters. But we are looking for the magnifying power. So from the formula of the magnifying power, when the image is at infinity, we have m as v naught over f naught minus 1 times d over fe. This is what we derived. So we shall have that, but d is going to be negative of 25 centimeters. This time around we are putting in the negative because in the other formula we are not considering it. We do not consider negative for the d here, so when you're substituting you shall consider it now. So we shall have that giving us m as negative 111.875. That's the magnifying power. Shall neglect the negative and conclude that the required magnifying power is going to be 111.875. Yeah, thank you for your attention. We meet in the next lesson.